finish up information about limits as x approaches different values, and we're going to look at what happens as x is approaching infinity. So instead of saying it's approaching 0 or it's approaching 1 or 3, what happens as x approaches infinity? Graphically, how is that working? Algebraically, what's going on with the function? So we will discuss the limits of functions today as x approaches infinity. This chapter really does, it really is a great end of the year chapter because we're going to be pulling concepts back from chapter 2 and looking at some shortcut rules of limits. And then we're also going to discuss sequences, creating some terms of a sequence, and then looking at the limits of a sequence. The homework today is back in the book. The rest of the week will be worksheets that I've made. But today is in the book for section 12. This is actually 12.4. We skip over 12.3 and we'll pull that back in next week as the last section that we cover. I will say most of this homework, you'll see it's not really work that you're doing, but it's understanding those 3 shortcut rules for limits. So minimal work. You might be asked to find a couple terms of a sequence, but that would really be the only work that you're really doing for these concepts that we'll look at. Little reminder, the worksheet is due tomorrow that we were working in class yesterday. And I think about 8 of you have that submitted, which is awesome. You got it done already. But that is due tomorrow. It's worth 8 points, not 2. And I have been looking and grading them, making comments on them, giving you feedback on them. And then Monday is the limits test. Thursday, Friday, those of you that'll be taking Keystones, we'll talk to you. If again, you think on Friday, you want to get that limits test out of the way because you're taking the Keystone on Monday, then you can definitely do that because we have 3 days like this week that we're just reviewing in class. So if you have a study hall later in the day on Friday, maybe you want to take it then, or you can do it next Tuesday.
Is tomorrow just a review?
Yes. So tomorrow, I will probably go over 1 or 2 questions from the homework that I thought were kind of neat. And then I'm going to start the worksheet with the class tomorrow. So yeah, tomorrow's just review.
Okay.
Yep. Darby, you don't have a question. Okay. All right. So if you want to look at section 12.4, where we're talking about limits at infinity. If you want to pull out your calculator as well, we're going to graph this function in the calculator and see if we can get a little sketch to look at. A lot of limits, you're looking at a graph, but then trying to think of the algebraic aspect behind it. In your calculator, I wrote the function here, f of x equals x over the quantity x minus 1. When you place that in your calculator, make sure you're placing the denominator in parentheses so the calculator knows that x minus 1, both terms are in the denominator. And then see if you can get a little sketch, give yourself a little diagram. Doesn't have to be a super precise sketch, but you can put a couple of points on there, get an idea of what's going on with the graph. And then we're going to look what happens as x goes to infinity and x goes to negative infinity. So if you can answer those 2 questions that are next to it after you look at your graph, what happens is x goes to infinity and x goes to negative infinity. So your graph should look something like this. This is a graph of a hyperbola. There are two branches. So this would be the algebraic hyperbola that we would have graphed in chapter 2, not a conic hyperbola, but still a hyperbola with branches. And you can see that those branches are definitely horizontally flattening out, but also vertically skimming along a line. So the question says, as x approaches infinity, so x going to infinity means we're going to the right side of the graph. What is f of x approaching? Remember, f of x is the same thing as y. Peter? 1. Because as I'm going out this way, the y values are getting closer and closer and closer to the number 1. They're kind of just skimming along the y value of 1. Peter, as x goes to negative infinity, which is out this way, the y values are getting closer and closer to 1. Peter, do you know what's happening at the y equals 1 value? That's an asymptote. So really, right here at y equals 1, we have an asymptote. That is the definition of an asymptote. If your graph, the x values go to infinity or negative infinity, there's an asymptote created in the graph. So x is skimming along a horizontal line as it goes to infinity. There is an asymptote located in that graph. So we would say then, talking about pulling limits in, the limit as x approaches infinity of my function, and I'm just going to cheat here and write f of x, is equal to 1. So as my x is going out to infinity, the limit of the graph is getting closer to 1. Or as x approaches negative infinity, the limit of my function, again, is getting closer to 1. And that's because they're getting closer to that asymptote. Anytime the graph approaches a y value, we can also say that is the limit of the graph. So there's an asymptote there that's forcing the graph to perform in a specific manner. The y value of the function is also the limit of the function. So instead of looking at a value of x in the actual function, which is usually what we do because we approach the value from the left and the right, now we're looking at the value as the x value is going to negative or positive infinity. So the definition of a limit of infinity or at infinity. So the limit as x approaches infinity of a function f of x could be noted as L sub 1. Or the limit as x approaches negative infinity of f of x. It might be the same, it could be different, it just depends, but we'll just say L sub 2. Depends on what the graph is. So limits exist even though x is going to infinity. A limit can still exist. And it's going to exist if there's an asymptote, horizontal asymptote in the graph, because that's your y equals value, and that's what a limit is. So your limit is the y of your graph at a specific x of your graph. Well, in this case, we're going to infinity and negative infinity. So there is a second function underneath here. This is a more formal kind of notation of a limit. So we're looking at the limit as x approaches infinity of the function 1 over x. So if you need to place that in your calculator, remind yourself what that graph looks like. This time, it should still be a hyperbola with 2 branches. But now those branches are approaching a different y value. And we're changing the function a little bit. So this function is just 1 over x, where the function above was x over x minus 1. So this is asking you to just look at the limit as x approaches positive infinity. which means I'm looking at this side of the graph as x is going to positive infinity. Not the negative infinity, just the positive infinity. So Hannah, the limit of my function as x goes to positive infinity would be 0. Yeah, that's equal to 0. And that is because there is a horizontal asymptote at y equals 0. My y values will continue to get closer and closer and closer to 0 because 1 divided by a big number makes a really small number. 1 divided by 100, 1 divided by 1,000. My numbers just get closer and closer to 0. So that would be the limit. So as it says, notice as the values of x get large, the fraction of value gets smaller and smaller, and it approaches the number 0. So a small number over big number makes a small number. Underneath in example 2, we have the limit as x approaches infinity. And then we're looking at 4 minus 3 over x squared. And instead of graphing this in the calculator, we're going to try and apply some properties of limits. And I want you to think about this as really being 2 separate functions. This is the function 4 subtracted from the function 3 over x squared. And we have some operations with limits that say you are allowed to separate this and look at just the limit as x approaches infinity of the first function. Subtract the limit as x approaches infinity of the second function. So that's operations of limits. If you're subtracting 2 functions, the 4 minus the 3 over x squared, you can find the limit of those functions and then subtract that. So we're using properties of limits, operations of limits. So let's think about this first one. The limit as x approaches infinity of 4. We're going to evaluate this first limit here. So think, what is the y value of the function? Because that's really what the limit is. So if you have the limit as x approaches infinity of 4. Cole, what's the limit there? Why is it just 4? Yeah, y is just 4. You have a horizontal line. So you can't plug anything in for x because y is always 4. So wherever x is going, whether it's 2 or 4 or infinity, the y is always just 4. Now, I want you to think about this second one. We have the limit as x approaches infinity of 3 over x squared. You can plug numbers in for x here. What happens as you plug numbers in for x? What does the value of the fraction become? What does it get closer and closer to? So think if you plug in a 1, a 2, a 3, a 4, I plug in a 10, I'd have 3 over 10 squared. I plug in 12, I'd have 3 over 12 squared. What's the value of this function get closer and closer to as you plug bigger numbers in for x? 0. So I'd be taking 4 minus 0. Because if I plug numbers in here, I'm going to have 3 over a huge number. And that's going to give me a limit of 0. So the larger the number you plug in to the denominator, if it's an x down there, the smaller the value of your function becomes. So the limit is just 4. The first limit is 4. The second function has a limit of 0. When you subtract them, you get the limit of 4. So you don't necessarily need to look at a graph if you can think about what's the value of the function. How is that changing as x gets bigger? Questions. So don't actually subtract them, the functions themselves. Don't try and create a new function. Instead, just kind of separate them and look at them individually. And that would be properties and operations of limits that you can do with the 2 functions inside. So I said we were going to talk about some shortcut rules of limits. There are 3 shortcut rules of limits at infinity. And if you look at the 3 functions that are here, notice that they're all in fractional form. The shortcut rules for limits at infinity deal with the shortcut rules for asymptotes. Specifically, those horizontal asymptotes that we found in chapter 2. So go back in your brain, think back to chapter 2. Let's look at this function here. So we have 2x plus 1 over x squared plus 3. If the shortcut rules for limits at infinity are directly tied to the horizontal asymptote, does anybody remember one of those horizontal asymptote rules? Thinking about the function that's given, or look at the 3 functions and kind of notice what's going on with those 3 functions. What do you look at when you're determining where the asymptotes are located, Jack? That would be for the vertical asymptote. So a vertical asymptote is found by setting the denominator equal to 0. Jenny? Yeah, so the horizontal asymptote is found by comparing the numerator versus the denominator's power or degree. So Jenny, in number 1, how would the degree of the numerator compare to the degree of the denominator? Yeah, so the degree, and I'm going to abbreviate numerator, is less than the degree of the denominator. When that happens, Jenny, where was your horizontal asymptote? It was at 0. So the degree of the numerator less than the degree of the denominator meant our horizontal asymptote was at y equals 0. Now that means that our limit is equal to 0. So the horizontal asymptote is the y value that's controlling the function as x goes to infinity. So this would be equal to 0. So when the degree of the numerator is smaller than the degree of the denominator, your asymptote is always at y equals 0. Therefore, your limit is equal to 0. So Kaden, looking at number 2, what's going on with those powers? Yeah, they're equal. So the degree of the numerator is equal to the degree of the denominator. Kaden, that horizontal asymptote was where? Not at 1. What did we have to compare when they were the same? The coefficients, yeah. So the coefficient of the number on top versus the coefficient of the number on the bottom. So I'm just going to write it as A over B. So that means our limit would be the coefficients as well. And if you want to remind yourself it's the coefficients, you can. So Kaden, in this case, the limit of our function 4x squared plus 2x over 3x squared plus 1 is 4 over 3. So the degree of the numerator is equal to the degree in the denominator. Then you're taking the coefficients of those degrees. Power on the top over the power on the bottom. The last one, we have negative 3x cubed plus 2 over x squared plus 7x. So if we compare those, Parker, what would you say is going on with these powers? Yeah. Do you remember what happened with that asymptote? Jack? Yeah. There was no asymptote. Does anybody remember what kind of asymptote there was? if there wasn't a horizontal asymptote, if that didn't exist, what kind of asymptote did the graph have? Could have a vertical, depending on the denominator. There was 3 asymptotes. So we had a vertical, we had a horizontal. If there was no horizontal, then there was the 3rd asymptote. The slant, nice job, Jack. There's a slant asymptote. So the slant asymptote was the line, y equals mx plus b form, going through the graph diagonally. So a horizontal asymptote does not exist. Therefore, the limit does not exist either. Because there's not a y value that the function is going to skim along. So if there's no y value for the function to get closer to, then there is not a limit. So that limit does not exist. So the little notice is what I kind of wrote above here, which I wrote it above instead of writing it below. We'll put that here. So notice that these follow the shortcut rules for horizontal asymptotes. So I think you could quickly do the examples underneath, which is what most of your homework is like. So see if you can find the limit of the 3 examples underneath here. Those 3 functions. So once you pull all of the limits together, which we'll do tomorrow, the key thing is going to be looking at what is x approaching. So if x is approaching infinity, then I can apply one of these rules. If it's not approaching infinity, then we have to look at the graph or think of an algebraic method that we can use to alter the appearance of the function. But if it's going to infinity, one of those 3 rules will apply because that would then be creating the asymptotes, Darby. There's really not much work you can show. Yeah. So Darby, what'd you say for letter A? Yeah. So looking at those exponents, the degree of the numerator is larger than the degree of the denominator. So that limit does not exist. Sorry, chicken scratch there, writing quickly. Joe, how about letter B? What's going on there? And why would it be 0? And then Jeremy, the last one. Yeah, negative 2/3. And that's because the degrees are the same. Pretty straightforward, as long as you remember the rules for the asymptotes. Questions? So the last thing that we are going to look at is we're going to look at some sequences. Sequences are patterns of numbers when numbers are in a list. So I have a list of numbers. I want to find the limit of the list of numbers that have some type of pattern to them. A sequence continues forever. So I could have a sequence of 2, 4, 6, 8, 10, 12. That's a sequence. It's a list of numbers that have a pattern. They're all increasing by 2. Sequences go on forever. Some sequences have limits and some don't. So we're going to see if we can look at the limit and decide, does the sequence have a limit as x approaches infinity? Our function or our sequence as x approaches infinity is 1/2x. Now you'll be asked to evaluate the limit of the sequence in 2 different ways. You'll be asked first to find a few of the terms in the sequence. The terms of the sequence are just the numbers 2, 4, 6, 8, 10, 12. So if I wanted to find the first, let's say 5 terms of this sequence, how would you find the first 5 terms of this sequence if my formula was 1 over 2x? So how could I find a term in the sequence or a number in the sequence? Anybody have an idea how I could get a list of numbers that would be represented from 1 over 2x? Check.
Is that like P over Q?
You could do P over Q, but you're making it way too hard. Jenny? Yeah, so if I wanted to find a term of the sequence, x is my variable. So I want to get a list of numbers that would be represented by that. Think of it as an equation. Well, I could plug in numbers for x. So if I plug a 1 in, Jenny, if I plug 1 in for x, I get, and then if I plug a 2 in, you get a 3 in. I'll do 5. So the next one would be, sorry. No, no, I understand how that could be confusing. I meant we would do the first 5, my fault. So these are called terms of the sequence. They're found by plugging in numbers for x. So if I want to find the first 5 terms, I would plug in the numbers 1, 2, 3, 4, 5. If you look at those numbers, what would you say those numbers are doing? What are they getting closer and closer and closer to? 0. So because the terms of the sequence are getting closer to 0, the limit of the sequence is going to be 0. We use a special word when it's a sequence, and it's converging. They're getting closer and closer to the value of 0. So we say they converge to 0. Fancy name. The limit is 0. So that is one way that you'll be asked to evaluate the limit of a sequence, by finding the terms and looking at the terms. The other way to evaluate the limit is to apply the 3 rules at the top, because it's still a rational function. The degree of the numerator can be compared to the degree of the denominator anytime it's a rational function. And notice that there's just a 1 on the top. That's a number. So there's not an x on the top. That means the degree of the numerator is less than the degree of the denominator. Therefore, the limit is also 0. So you can kind of apply it 2 different ways depending on what the question is asking for. If it just said find the limit, then I can apply the limit at infinity because my x is going to infinity. Or I can list the terms of the sequence. So let's look at the next example. I think there's a couple more, yeah, 3 more on the other side. If a sequence does not converge, it's said to diverge. So converge means they're getting closer to a number. Diverge, they're not getting close to a number. They're going in opposite directions. In this case, we have a 1 and -1, a 1 and -1, a 1 and -1. So that sequence is just going to go back and forth between those 2 numbers. So we say this diverges. This actually oscillates. So we talked about oscillating last week, where it's just going back and forth between 2 numbers. So it says it's diverging, but it's actually oscillating as well. It's going back and forth. So this sequence, we would say the limit as x approaches infinity, and I'm just going to say f of x does not exist. There isn't a limit. It goes 1, -1, 1, -1. Remember, it has to go to the same number to be a limit. So in example 4, it says to find the first 5 terms of the sequence and then find the limit. See if you can calculate the first 5 terms. Sequences are usually defined with the variable n, and that is the actual variable that's being used in the next 2 examples. So as n approaches infinity, we have 2n plus 1 over n plus 4. So to find the first 5 terms, you would plug in a 1 to find the first term. So I plug a 1 in, plug a 1 in. you'd plug a 2 in to find the second term. Only thing that's changing is the n. So if I'm finding the second term, that's what n represents. So then I plug a 2. And then I would plug a 3 and then a 4 and then a 5. So see if you can find the first 5 terms of this sequence. So you're taking the formula or the equation and you're just plugging in whatever you're asked to find. So if I want the first 5 terms, I'm going to plug in the numbers 1 through 5. Each one of those values will give me a term or a number for the sequence. So Kaden, the first term of our sequence would be, and then the second one, and then, because that's 7 sevens, the next one, and then the last one is 11 over 9. So the question then says, if I have those terms, so my terms 3/5, sloppy, 5, 6, 1, 9/8, 11/9. Find the first 5 terms and then find the limit of the sequence. So by looking at the first 5 terms, you can see that the number on top is counting by 2. The number on the bottom is going up by 1. But by looking at those first 5 terms, kind of deciding what the limit is might be a little tricky to kind of think about because I only have 5 numbers to look at. So instead, if you look at the equation as a rational function, Kaden, how does the degree of the numerator compare to the degree of the denominator? They're equal. So yes, I can look at the numbers of the sequence, but sometimes those first 5 terms aren't going to tell me a lot. So instead, if I compare the degree of the numerator to the degree of the denominator, then I can find the limit in that manner. Kaden, if the degree of the numerator is equal to the degree of the denominator, then this limit is 2. So I'm looking at the 2 over the 1. So that limit would be 2. Another way to find it, you could plug in like 50, you could plug in 100, plug in bigger numbers. Sometimes plugging in a bigger number might help see what's going on with the fraction. But by looking at those fractions and just those first 5 numbers, you probably wouldn't think that those limit is going to be a 2 just with those first 5 values. So the last one underneath, find the limit of the sequence whose nth term is defined as this. So this a sub n, that's just sequence notation. So this is actually how we kind of define a sequence. So instead of saying f of x for a function, a sequence can be noted as a sub n. So this one wants us to find the limit of the sequence. So our goal is to find the limit as n approaches infinity of this sequence 8 over n cubed. And then inside we have n plus 1, 2n plus 1 all over 6. It's a big equation. It's not asking you to find the first 5 terms. It's just saying determine the limit of the sequence. How could you determine the limit of this huge function? Peter, what could you do? Yeah, so he said, distribute, multiply those terms together and compare the degrees of the numerator and the degree of the denominator. So if we look at the inside here, Peter, and you FOIL n plus 1 times 2n plus 1, what does that give you when you FOIL that together. So 2n squared plus 3n plus 1. All of that still being multiplied by n. So that means we would have 2n cubed, 3n squared plus n over 6. So we're doing a little bit of algebra here, distributing. And then Peter, what does your final function become? So he then distributed 8 to the numerator and the n cubed to the denominator. So this is our new function or our new sequence. Peter, what would the limit of this sequence be as n approaches infinity? Yeah, so you get 16 over 6, which reduces to 8/3. Questions? So a sequence is a pattern of numbers, but really a sequence is another way to write a function. It's just a list of terms that form a pattern of numbers. So your homework will contain some problems that you're just going to find the limit as x approaches infinity using the 3 different shortcut rules. Some of them will then contain finding patterns or terms of a sequence and then finding the limit based off of those terms or by using the shortcut rules. Questions? So as I said, tomorrow we are going to review. Thursday, we're going to make some crazy piecewise functions on Thursday. We'll be graphing them ourselves, doing a little work with piecewise functions. And then Friday, we'll just do more review. Have a fantastic day.